Hello, everybody, and welcome to Ionbond's webinar for food coating solutions. My name is Michael Helms. I'll be your host today and presenter as well over the next 30 minutes during our discussion. Joining me are two colleagues from Ionbond, my colleague, Dr. Antonio Santana, head of the medical and food group at Ionbond, as well as Jan Schmohorst, who is the sales manager for Ionbond in Switzerland. So welcome, gentlemen. Thank you for joining us today. We've also arranged a chat box. So if there's any questions from anybody during the call, you can feel free to drop us a note. And at the conclusion of the webinar today, we'll have an opportunity to get into the next phase of the discussion. So the agenda that we'll be going through today we'll talk a little bit about the introduction to Ionbond. We'll also go through the FDA approval process as it pertains to the coating properties. We'll also go into a little bit more in-depth discussion pertaining to the coating technology overview, as well as we have some examples of some case studies and features and benefits of some of our coatings in these applications. And then at the conclusion of today's discussion, we have a Q&A session arranged. So with that, I'd like to transition over to Jan.
From my side to the IHI Ionbond webinar on food contact applications. A few words about IHI Ionbond from my side. We are a coating treatment, a surface treatment company. We coat the customer's goods with our coatings, and we apply them by means of PVD, CVD, and PA-CVD. So we are job coaters. Being a job coater means that we have to be close to our customers. I wanted to show the next slide. Here it goes. Being a job coater means that we have to be close to our customers, so they don't have to go a long way to reach our coating centers. And with a global presence of 35 coating centers in 15 countries, we show a nice global presence. So having a look at the map, we have 11 facilities in North America. We have 18 in Europe. And going further east in China, we have 4, India, we have 2. So wherever you are, we are probably close by, and you can reach out to us for getting your goods coated. So why do we do vacuum deposited coatings? With these coatings, we can give the base materials, which have their required characteristics, complete new characteristic when it comes to the interaction with the outer world. So we have, for instance, let's take the milling drills on the right side. There we have the steel substrate, the steel base material. This material is brought into shape, and this material, and with the shape, is already a pretty good tool. But with the coating, finally, we can grant this extreme high hardness, this low friction value, and the good wear resistance to have a very long-lasting tool. And another example is the knee implant. You can see as the second to the left. This golden colored object, this is the lower end of your femur bone in the leg. And as we grow older, it happens that this part of the leg or the bone is worn off, and then we have problems to walk. So with this knee implant, we will be able to walk further for decades. And the knee implant, again, is made of substrate material, which is the perfect material to fulfill the mechanical characteristics of this implant. But with the coating later on, we get this smooth surface, and this smooth surface creates a low friction towards the to the rest of the knee, and we have low wear resistance, and it's biocompatible. So the excellent raw material or base material together with the coating makes this object being a really good object. So with the coatings, very demanding parts, very demanding products, we can give an additional value which makes or multiplies the functionality and the lifetime of these articles. The coating service portfolio shows the various industries we are providing or we are supplying with our coatings. In the end, coatings are used in almost each and every industry. To show you just a few of them, the cutting tools might be the oldest and the most famous application of this vacuum deposited coatings. We all know the drills. We might buy in the shops the drills with the golden tip. This golden tip is thin film coating. This is titanium nitride. And with this coating, we can create a very long-lasting tool. Forming and molding tools, as another example. Here we can speak about the seaming rolls, which are used for canning beverages and food cans. And these seaming rolls, they need they have a pretty small tolerance. And this small tolerance is required to actually close the cans airproof, gasproof, liquid-proof. And when you use the seaming rolls and the shape of the seaming rolls changes, the cans are not closed properly any longer. So with the coating, we can increase the lifetime of the seamers to a maximum and reduce the downtime of the machines. Coming to another important application, this is the medical application. We have seen the knee. Again, with the coating, we multiply the lifetime of the goods, and the coatings are biocompatible, and for these reasons, they are used to a large extent in the medical field of the industry. And our topic for today is the food contacts. All these examples I talked about in the seconds before are valid examples for food contact materials as well, because we need a high hardness, we need a low wear resistance, we need biocompatibility, and we might need for some applications low friction as well, amongst others. And those are the potential, or those are the applications we are fulfilling and we are providing and we are serving with our coatings. And in this moment of the presentation, at this point, I would like to hand over to Michael to tell us a bit about the FDA coatings. So, Michael, are you ready?
Yes, thanks so much, Jan. So let's move on. So talking about the next application, what we're showing here is these are all of the coatings that we're going to be presenting to you is in this portion of the presentation have all been gone through the Food and Drug Administration regulatory testing. So this is an example of the documents that we will prepare to furnish to you if we move forward with a given application within your business. These are the coatings that we have selected. So to give you an example of what you're seeing here on the table, on the left-hand side is a description of the coating. So all of our coatings, we have a trademark name. So for example, Ionbond 01. And then next to it is going to be the chemistry or the composition of the coating. So in this instance, it would be titanium nitride. We'll discuss a little bit more in detail on the layer structure. So the layer for titanium nitride, we would consider as a monolayer. Adjacent to that will be the FDA TOR or certificate number that would reference to that particular coating. Typically, if you're not familiar with these types of coatings, these are normally thin film coatings, as we would call them. So they can be anywhere from a thickness range between 1 to 10 microns. And then also as a result, these coatings have unique functional properties associated with it. So as you can see here, the friction coefficient of titanium nitride is around 0.5. And the micro hardness, we measure micro hardness in all of our coatings in Vickers. So here we could be typically in a range, depending on the structure of the coating, anywhere from a range of around 2,500 to 3,100 Vickers. And then also an attribute associated with each of these coatings is combining the different elements, which we'll go into a little bit more in detail in the follow-on materials. You'll have a color. The color would be gold in this case. And again, it's very consistent, as you can see coming down through for our Ionbond 30, which is chromium nitride. Again, another monolayer coating. Ionbond 42, which is a DLC or a diamond-like coating, some people would refer to it. That would be a multi-layer coating. We'll discuss that in a little bit more in detail. And then last but not least is our Ionbond 43, which is an amorphous diamond-like coating. So to give you an idea, as I was explaining before, some of these coatings have unique color properties associated with that. So if you're, again, not familiar with these coatings, if you're looking at this chart, in the center of the column, you'll see gold. So the titanium nitride would be very close equivalent to the gold or 24 karat gold color. If you were looking at the DLC coatings, whether it be Ionbond 42 or Ionbond 43, they would fall within the black color spectrum. So anywhere from an anthracite to a dark black. And then for the chromium nitride, that would fall more into the gray color spectrum, and that would be closer to more of a stainless steel related color. Going in and talking a little bit more in depth with regards to these coatings is we use, at Ionbond, we use three different technologies to grow these films. The first method is known as PVD, which stands for physical vapor deposition. The other process we use is referred to as PACVD, or plasma assisted chemical vapor deposition. And then the other process is CVD, or chemical vapor deposition. Below that, you'll see the periodic table. All of the coatings that we apply and that we develop, they all originate and start from various different elements on the periodic table. And by combining these together, they have unique attributes that have these performance characteristics of either high hardness or perhaps low coefficient of friction. To the right-hand side, you'll see two SEM images. The image at the top of the screen that we identified as a monolayer, this is a cross-section of a coating that we've done. And what we're trying to show here is at the very bottom, as you can see in the graph, that would actually be the substrate. And then on top of that would be the coating. So in this instance, that could be the titanium nitride coating. Below that, you'll see a coating that we would refer to as a multi-layer coating. Again, at the bottom, the very bottom of the structure, you will see the substrate that we would be bonding the coating to. And then from there, you will see the first interlayer. So that could be a chromium or a chromium nitride. And then on top of that, that could be a DLC coating on top. And what we're really looking for in this example is the very smooth surface finish on that. This just goes into a little bit more in depth of the structure and how we are able to derive the various different bonding layers and the functional properties at an atomic level of these films. We would refer to some of these as could be an sp3 type structure or sp2 structure. I won't go into too much in-depth discussion in this area, but if you're curious and you'd like to learn more about this, we can address that at some point at the conclusion of the presentation. So, we ask is why titanium nitride or chromium nitride or DLC in food-related applications? Based on our experience, as Jan had pointed out, we have an extensive amount of experience in industrial component applications, forming and molding applications, cutting tool applications, very high performance wear-related applications with many similarities to the food industry. So as an example, we found and we felt that for abrasion resistance and in an effort to reduce wear, maybe in cutting or forming, for example, of potato chips, and Antonio is going to go into more discussion about that in his presentation, one of these coatings might be very well suited for that. Same goes as if we are dealing with situations of trying to reduce or anti-sticking related areas. So we all know in some instances that food has a tendency to stick to tools and machine components during processing. It could be pastas, it could be various different type of dough or confectionery products. Also there's some instances where it may be difficult to put some type of lubrication into certain areas. Again, due to the functional properties of some of these coatings, working in a dry condition, they will provide the same type of lubricity that you would normally have to, where typically a liquid or a fluid would normally be required. I have coming here is a series of graphs. Just wanted to show again some of the properties of these coatings. So in this example is where we're trying to depict is to show higher hardness equals less wear. So if you're looking at the table or the graph, you'll see on the left-hand side the hardness Vickers scale. And across the bottom, you'll see various different types of materials. So we've really gone from the left over to the right. You'll see, for example, steel. This would be uncoated, maybe nitriding, perhaps a process that you've used, or maybe hard chrome plating, or WCC in this instance. And then showing next is coming in with some of our different coatings, for example, like the Ionbond 30 chromium nitride, or Ionbond 01 titanium nitride, and then getting all the way down to our Ionbond 43 amorphous DLC. You can see how the hardness properties will improve based on applying a coating onto a bare substrate. In the nest example, what we wanted to share with you is how our coatings make surfaces easier to clean. So these coatings do have hydrophobic properties. And basically what you're seeing in this particular graph is the contact angle on the left-hand side. And you can see that starting on the right-hand side of the graph and working to the left, where the Ionbond 43 coating comes into play, 42. And as you can see, based on the properties of these different coatings, how the surface contact angle changes and demonstrating the hydrophobic properties of these films. The other piece we also wanted to share with you was some of the characteristics for the anti-sticking. So again, what we're trying to show here in this particular graph is on the left-hand side is the coefficient of friction. And again, using the same standards that we had used in the previous materials of steel, so uncoated on the left, nitriding, hard chrome, tungsten, and then the various different Ionbond coatings that we've been discussing. And as you can see, by applying one of our thin film coatings, how we can really substantially help to reduce the coefficient of friction over the particular component. So some of the target applications we'll be discussing in the next piece is really coming into maybe applications that could be considered for these coatings could be tanks, panels, short pipes, pump components, cooking devices, perhaps an anti-scratch surface. In food packaging, it could be coatings on seaming rolls, as Jan had explained earlier, for manufacturing, and also for food processing molds and toolings. So this could be extrusion molds and components, could be milling, grinding wheels, and the lamination process. So with that, I'd like to bring in Antonio or Jan, and maybe you could take us through the coating technology.
Okay, thank you very much, Michael. So let me switch on to the next slide. So the coating technology overview. Michael said it, PVD, CVD, PA-CVD. I would like to illustrate a bit what Michael was saying. So we have three coating technologies, and let's start with the physical vapor disposition, which is also known as the PVD. In PVD, we bring the parts in the chamber, in a vacuum chamber. We evacuate the chamber. We create a pretty high vacuum, and exposed to this vacuum, the pure and very reactive surface of the parts is getting exposed, because usually in daily life, all the articles, all the surfaces are covered somehow with gas or with water. And when you bring them into the vacuum, they're getting completely exposed and they're getting very highly reactive. And next, we have this targets. This is how it is called. The targets made out of the solid material, like, for instance, titanium. Those are marked in this graphic with the red bars, 1 on the left, 3 on the right. And by means of an electric arc or by sputtering, we can evaporate, or we can remove parts out of the surface of the targets. And these electrically charged particles, titanium particles in this case, they are then getting accelerated by an electric field to the surface of the goods to be coated. And once they arrive on the surface, they will adhere to the surface and get part of the surface and form the coating. So what we can do in addition is you can see it on the right top corner of the graph, we can add reactive gases to the vacuum. And if we evaporate titanium on one side, we might want to add nitrogen. And together with the nitrogen, the titanium will then form titanium nitride as a coating on the surface. And this titanium nitride, we all know, this is this yellow coating we find on the drills. It is a line of sight process, which means since we have to apply an electric field to make the titanium ions move from the target to the parts, they will arrive on the parts where the electric field is, and this is somewhere between the target and, well, it is between the target, this electric field, and the parts, which means we cannot coat bores, we cannot the inner surfaces of a cylinder, and we have to rotate the parts in many different ways. We can have single rotation or multiple rotation to have a very smooth and homogeneous coating on the surface in regards of thickness and in regards of aspect. So this is so far the PVD, and the next technology is the chemical vapor. No, hold on, we have a nice video. This is a beautiful PVD coating machine from our sister company Hauser. If you would like to estimate the size of the machine, you can have a look at the screen on the right-hand side. Now it's gone. And now with this X-ray view, we have a look inside of the coating chamber. You can see the goods on the turntable rotating, and 3 targets on the left and 3 targets on the right-hand side. And so this way we can observe in this demonstration how the coating takes place. Once again, we can maybe get a glimpse of the screen to estimate the size of this machine. Next slide is up to me to switch further. So the CVD, the chemical vapor deposition. In chemical vapor deposition, vapors are chemically reacting in the reactor, and this chemical reaction, or the result of this chemical reaction, then is the coating of the parts. Coming from left to the right, well, it is important to say that we don't have a target which we evaporate. All the chemicals, all the vapors which need to be deposited are filled in the reactor as vapors already. We have different precursors. We have gaseous precursors, we have liquid precursors, and we have solid precursors. The gaseous precursors here, for example, the hydrogenium or the hydrogen chloride, we can add straight because they're already gases. Liquid precursors and solid precursors, they need to be evaporated prior to filling them into the retort. The retort or the reactor itself, this is the gray dome we see in the middle of the picture. This is made out of steel, and a heating cap is placed over this dome, and with the heating cap will heat up the reactor. We fill in the vapors, and the chemical reaction is taking place, creating the coating on the parts. It is actually a flow of vapor, flow of gas in the reactor. We are pulling these precursors by means of the vacuum pump through the reactor and out of the reactor again. And this way we can create a mixtures out of gases, and create multi-layers. However, after having reacted in the dome, these gases are condensated and neutralized, and clean air or cleaned gases then are ventilated out of the system. In contrast to PVD, the CVD is not a line of sight process. So with the CVD, we can also coat inner surfaces of goods or drill holes, for example. So CVD is adding complementary coatings and applications to the PVD coating portfolio, so to say. Okay. Next, and this is something which is me personally fascinating a lot. This is the plasma-assisted CVD. On the first look, it looks pretty similar to the PVD. We have the vacuum chamber. We have the goods placed on tables. We have a high-frequency connection to the table, and we fill in the reactive gas or traces of the reactive gas in the vacuum chamber. And then by radio frequency, which is feed into the goods, as you can see from below, we can start a plasma sheath, which is around the goods to be coated. And in this plasma sheath, a chemical or a physical reaction is taking place. And the graphite or the carbon, which is filled into the chamber, is then transformed into graphite and diamond atoms. And this mixture out of graphite and diamond atoms then is creating coating, which we call DLC, diamond-like carbon, which is an extremely smooth, amorphous, and very hard coating. And we can do this at relatively low temperatures, and the results are really outstanding. So PVD, CVD, and PACVD, those are the coating technologies we are using. And at this moment, I'd like to hand over to Antonio. And Antonio, how are you doing?
Good, thank you. Thank you very much, Jan, for this coating technology overview. Thank you also to Michael for the coating properties overview you gave. And also thank you to the audience to stay with us and to listen to what we want to tell about food contact coatings. I would like to remind the audience that there is a possibility for you to ask questions. You just have to drop them in the chat box, and so that we can, on the QA session, then address the questions you have. So in this chapter 4 of the presentation, what we would like to show is some case studies showing the benefits of applying the coatings that Michael was explaining the properties, and what Jan was showing how to make them. And the first case here, we have the concept of sanitation of food contact devices. Overall, for this type of application, what you need to have is biocompatible materials, surfaces that are easy to clean, and as much as possible to not use grease or lubricants in order to keep your system clean. So our coatings, especially the diamond-like carbon coatings 42 or 43, are strongly recommended to achieve this goal. Why? Because there is a friction coefficient which is low. You can actually apply the coating on surfaces in contact with each other in order to reduce the friction between these two. We have also tested these coatings against biocompatibility standards ISO 10993, and they have proven to be biocompatible. As well as we have also seen that these coatings are very stable because they really stand strong alkaline chemicals when cleaning or disinfection or even sterilization cycles. So by using our coatings, you kind of achieve better sanitation of your system. They will become easier to clean, easier to maintain, less time you take to maintain the system because you need to disassemble less often the devices that you have assembled. With the next case we have, it's about, we start a number of slides about mixing. Here we are showing solid liquid mixing. The example we are, let's say, focusing here is on a meat cutter system. For this type of application, we also recommend the use of the diamond-like carbon coatings. Why? Because they have the high hardness and they have the low friction. And with these two components, as you have seen with Michael's graphs, you have very, very, very low wear. So with these attributes, we see a 5 order of magnitude improvement when you have the system coated versus uncoated. On another mixing example here, we have the steam index mixing, where it is no longer a mechanical system doing the mixture, but also the temperature. It's used in cereals, puffed rice, and popcorn preparation, for example, among others. The temperature will basically extract the water from the substances. And what you require in this type of machinery is actually oxidation resistant surfaces that do not chemically change because of the presence of high temperature. And in this case, our coatings can help giving that stability. If you use titanium nitride, which is up to 450 degrees C, where it's completely stable. Also the chromium nitride, again, up to 700 degrees C. In this particular application, we do not think that diamond-like carbon can make it so well, as we see some tendency for structure change or loss of properties above 300 degrees C. So continuing on the mixing scenarios, we have for immiscible liquids, when we want to do emulsification or homogenization, for example, where the concept is to try to make them live together when they don't want to live together, reducing the size of the droplets. And for this, we really have to apply high shear forces, high pressures, high rotational speeds, high vibration, And this is very much energy consuming. And when we speak about energy, we also speak about heating increasing, the temperature increasing of the system. And in this today, some of these systems are actually have to be cooled, which is not making a design very simple. This type of application, actually, when we look at the drawing and with the scale having a slight difference, but it's very similar application compared to the injection pumps in the automobile industry, where we also apply successfully coatings like diamond, like carbon coating on these devices in the cars that we are driving every day. So this shows the technology is safe, and this explains why we, for this particular application, recommend the use of diamond-like carbon coatings, because they have this low friction coefficient. They will allow to produce less heat, so you can cool less, but also increase the pressures in the applications and consume less energy. Changing a little bit from the mixing now into real pure cutting. In the pure cutting in the food industry, we have mainly two scenarios. We have the scenario of cutting soft substances, fibers, so high sticking surfaces, and the scenario where we need to cut hard and abrasive surfaces. So for the first, we really recommend the use of diamond-like carbon coatings to avoid what you see on this scanning electron microscope to the top right of your screen, which is really material being sticked. So by the use of diamond-like carbon coating, you can avoid this. And by avoiding this, you also avoid the temperature to raise, and you can have a cleaner cut. In the case of cutting abrasive goods, like for example frozen fish, you should use then the titanium nitride, for example, where you have a higher resistance to the abrasion for this particular application. One high pressure at a larger scale application we have is the crushing, grinding, and milling. We have, for this type of application coating, which we recommend, is really the chromium nitride. It's a high hardness coating. It has a high fracture toughness. It is really, really indicated for high pressure and when you need really reinforcement of the teeth. In some cases, depending on the design of the teeth, etc., you can even reinforce the strength of chromium nitride by applying a diamond-like carbon layer on the top. And you see in the image in the center of the slide, actually how the coating, which is, and I remind the audience, the coatings here are really thin. We are talking about, in this particular case, a total 5 micrometer coating thickness, but this 5 micrometer will allow to increase the load carrying capacity and increase the overall strength of the tool and make really a better performance and increase the durability of the tool. In terms of packaging, our coatings, they are not materials used for the packaging itself, but they are used in packaging machinery. So there are basically two concepts here. We want to be sure the coatings are not migrating into the food, and also making sure that the coatings act as a good ion barrier, so that the materials that are used for the machinery, like many different grades of stainless steels, do not migrate into the food. Migration tests have been performed. We have seen that our Ionbond coatings do not migrate into food, so they can be used in packaging systems and food processing systems in general. But I also would like to add, and also as Jan has explained in his introduction, in the medical field, we have observed that actually not only the titanium nitride, but also the diamond-like carbon coatings are excellent ion barrier coatings. So by applying them on stainless steel surfaces, really achieve an ion barrier, which is important from a migration concept. So I think it is important to remember that when you don't have a coating, it's much easier for you to have chemical migration or wear particles going into the food compared to the situation when you have a coating. And as you could see, the hard coating is lowering the wear and improving the overall performance of the system. So that is really the summary of the applications I wanted to guide you through. In summary, we have seen the coatings are biocompatible, they are easy to clean, they lead to less maintenance in the systems where they are applied, they increase the durability of the components indeed. Overall, you have a situation where you have better sanitized systems where even the bacteria, I didn't go too much in that direction, but into the bacteriological proliferation is going to be reduced by the use of these inert coatings, which are, as I said already a few times, chemically stable. So overall, also we see the benefit of saving energy because the parts they move easier as you have less friction in the systems when they are in contact with each other. With this, we enter smoothly into the next section of the webinar today, of the questions and answers. I already wanted to thank you very much for listening to us today. You see also on this slide some of the contacts from Ionbond in the three different regions. This is not an extensive list, but you can immediately capture maybe some names that you would like to give a phone call in order to know more about the coatings that we provide. Yes, so thank you. And I would like to go back to Michael Helmens now, who is going hopefully read some of the questions we received from the audience.
Okay, thank you so much, Antonio. Thanks, Jan, as well, for your input today. We do have a few questions coming in on the chat box. I have a question here. One of the questions it's asking is there a size restriction, Antonio, of what type of parts can be treated in our systems?
Okay, so I can answer to that, as I think all of us can answer to that. Our machines, they are vacuum systems, so they are limited in sizes. I think that is the question, right? So we are talking about yes, component sizes which go up to, let's say, 1.4 meters long, and depending on the application, yeah, 1 meter diameter. So this is the largest vacuum chambers we have. And then, of course, we would have to look more in detail.
Okay.
You want
Antonio,
to complement the answer, Michael?
Yes, Antonio, another
Maybe?
question here. What is masking possible on parts? Can you mask a certain area on a component?
Absolutely. We can use masking, and that works pretty well. What we recommend in the masking is in general to be metallic, so that it is electrical conductive. Yes, and then if we have to see in more detail application by application, but masking is possible.
Okay, thank you. The next question we have is what coating is best for pasta extrusion applications?
Okay, so for the high pressure applications where the high temperature is not involved, we also would recommend here diamond-like carbon coating, so with low friction and high high load carrying capacity in the end. Yes, for the extrusion.
Great, thank
All
you.
right.
Antonio,
Any
we have
other
another
question?
question here. It says, do the coatings have flexibility for bending machine parts?
Yes. Our lowest elastic modulus is actually shared between the chromium nitride and the ADLC, amorphous diamond-like carbon coating. And as you can see, we can do compositions of chromium nitride and DLC. So yes, we among these four coatings, we have good candidates for following the elastic deformation of components. When it comes to plastic deformation, That is about space, and the coatings will be under such pressure that it might not be possible to use them. But under elastic regime, yes.
Okay, thank you.
Yes.
Antonio, we have another question. The question is do parts require fixturing within your vacuum chamber?
Yes. So as Ian was explaining to us, we have we have many different technologies, right? But in all the three of them, we need some sort of support for the components to be in the chamber. And in the cases where we need to have rotation, of course, the systems have to be adapted in order to have to allow the rotation. And as Ian was explaining, for the case, for example, of physical vapor deposition, it's a line of sight process, so we really need to rotate in order to make a uniform distribution on the component to be coated. So, but yes, we need fixtures. Mm-hmm.
Okay. Antonio, thank you. We have another question. The question is there any work in the manufacture of animal feed?
Not specifically more than in the canning, so on the packaging, that goes also to that industry, but not necessarily having a main focus on the pet industry, on the pet food industry. Sorry.
Okay. And then a subpart of that same question, Antonio, is what would your recommendation be for a coating on knives to cut feed?
To cut?
To cut feed.
Maybe I don't understand what.
What
okay.
type of
probably
coating would you recommend?
very sharp, very thin diamond like carbon coating. About cutting is always about coating thickness. It's very important to keep the thickness low, and so that we don't change the sharpness of the base material.
Okay, thank you.
If you want to compliment Michael,
that was sufficient. The other question is can you guys give an idea on cost as it compares to your coating process as it compares to hard chrome plating as a ratio?
Well, yes, it's difficult to say depending on the size and the volumes. Certainly, I mean, what we see is, and what we are able to do more and more in the stream that we see of replacing the wet chromium coatings and other coatings as well in wet environment with the vacuum technology, and also, as I said, we have vacuum chambers which are very large. So we are more and more competitive in that. I think for that precise answer or giving figures, we would like certainly to see the drawing, the geometry, and to look at the case study more in detail.
Okay, thank you. Antonio, another question is, are the coatings suitable for heated surfaces for preparing dough without burning into the material?
So this, as I gave the example on the mixing with the induced steam, so the coatings have their maximum service temperatures without changing chemistry. So if we and in cooking, it might be a little bit more complicated, depending on the temperature of the energy, on how the energy is distributed. But as I said, chromium nitride goes up to 700 degrees C. So up to that level, there is no real change in the coating chemistry and the coating volume. So, what can I say? The coatings are stable.
Okay, thank you. Antonio, another question is the DLC able to effectively withstand washing actions with hydrogen peroxide?
Yes, without any problems. So that is, I mean, often say to the audiences we are in thin film technology, so these type of questions about the coating and the coating resistance to many chemicals and so on, you should remember that if the coatings are 5 micrometers thick or 10 micrometers thick, you need to prepare the surface accordingly. You cannot have a surface which is not well prepared enough in order to receive such coating. You don't get the coating performance like a magic. So it's like you are having a performance with a thin film coating. So the chemical resistance is there as far as the surface, for example, in an RA would be 0.1 micron. So this just to give an example, not 3 micron array, for example, where that is not working anymore. We have too high roughness, and the coating will not cover properly the material. So if you really want that type of stability, you really want to also prepare the surface prior to coating.
But Antonio, sorry, the DLC itself is chemically stable.
Clear. Thank you.
So hydrogen.
Thank you very much. So one of the next questions, almost Antonio, kind of going on a point that you just made. The question is, what is the approximate roughness of the materials?
Well, so there are different ways of preparing the surfaces, right? I mean, we have the blasting, the mechanical polishing, electro polishings, etc. In general, up to 1 micron array, we can make a good job. Ideally, if you stay below 0.5 micron array is ideal, and everything you can do below that is fantastic. In this technology, it is vacuum technology. It's very clean in general, and the substrates also have to be exempt of residues. So if you use polishing medias or blasting medias in certain ways, the processes have to be validated, just or checked and controlled prior to our coating, so that we are not coating over residues that we should not be coating, and then the coating does not adhere to that residues. But it is very important, but that's of course the normal, let's say, procedure we have for applying coatings and making sure they are well applied.
Very good. Okay. I think, Antonio, we have one last question I see right now in the chat box. It is a pump application pertaining to a gearbox. It's an area where they're stating they see some vibration and also experiencing some galling as a result. What coating would you recommend in that particular application?
Yeah, so there I would combine the graphs that you have shown. You have shown that for anti-sticking, the diamond-like carbons are the best. Then you have vibration. You have a certain need of load carrying capacity. Being very precise in an answer to that question, I would say an Ionbond 42 multi-layer, so chromium nitride DLC, would be really the right answer for that type of application. Neither the pure DLC, neither the pure chromium nitride, but the multi-layer coating.
Okay, very good. It appears that that's the last question that we had coming in.
Okay.
So I'd like to take this opportunity to thank you, Jan. Thank you, Antonio. And most importantly, I'd like to thank all of our guests and audience that joined us today. I hope that the overview on Ionbond's capabilities in food contact applications was helpful and informative. And please reach out to one of your Ionbond local salespeople for further information. We look forward to working with you in the not too distant future. Have a wonderful day. Bye-bye.
Thank you very much, Michael. Thank you very much, everybody. Goodbye.